graphs. Tomorrow we're going to extend it from 1 dimension to 2 dimensions. And then we're going to get a little out of control. I like it. I like it a lot. And we're going to go ahead and get started. So, in the first column, yes.
Are there extra notes?
If there are, they would be in the top tray in the back. So in the first column, we're going to have a graphical representation of the information that you have been given in the second column, which is represented in set builder notation. We need to feel comfortable with set builder notation. And then given either one of these, we should be able to write it using interval notation. Now, I think set builder notation lends itself very nicely to interval notation, but we do need to be able to interpret it and put it in a graph. So if I look at the first example, the first example is saying that I have the set of all values x such that x is in between, all the values in between a and b. So if I have a, which is less than b, on the number line, and I want to represent all the x values that, well, are in between them, the endpoints would be open because I just have less than symbols, not less than or equal to, and I would shade everything in between those 2 points. So using interval notation, how would I represent that? Exactly. Now, going from the first example to the second example, what do you notice has changed?
There's a closed.
It's the or equal to here. So how is that going to impact our graph?
Closer.
It's going to be a closed circle at A, open circle at B, and shading everything in between. And if I want to represent that using interval notation, what would that be?
Bracket.
Exactly. Now, looking at the first example and comparing it to the third example, what is changed? The right endpoint is or equal to. So while I'm still looking at A and B on the number line, A is open, B is closed, and I'm still shading all the values of x in between those. So what would that interval look like?
Parentheses A, B, brackets.
Beautiful. So far, so good? Okay. Now, looking at the fourth example, bless you, I still have A and B, but describe the graph to me. They're both closed, and I'm shading everything in between. Beautiful. So again, the corresponding interval would denote that both A and B, the endpoints of that interval, are closed. Now, if you are given example 5, let's say. Now, some people like to always have the variable on the left. So I could rewrite this set builder notation as x being greater than A, correct?
Mm-hmm.
Okay. Some people like to look at that because then we can identify A on the number line and say, well, x is going to be all values greater than A. So I would have an open circle at A, and I would shade to the right. Now, if I wanted to represent that using interval notation, what would it be?
Open parentheses A, infinity.
Beautiful. And in number 6, again, I could rewrite this set builder notation where the x is on the left-hand side of the inequality. These are equal, different representations. And how does the graph change from the previous example?
Closed bracket.
A is closed, but I'm still shading all values greater than that. So similarly, I would close A, but, oops, not B, infinity.
Infinity is always open.
Infinity is always open. Now, looking at the next example, I have set builder notation saying that I'm looking at all x values that are less than b. So B is open, and I shade all values less than B. So that would be negative infinity to B open. What changes to the next graph?
B
less
is
than or
closed.
equal to.
Okay, so B is closed, but I'm still shading all values to the left.
Can you scroll down?
Yes. So far, so good? Okay, what would I graph on the number line if I'm representing the set of all real numbers?
Negative infinity,
A line.
positive infinity.
The entire
Yeah.
real number line, right? And what would the corresponding interval be?
Negative infinity, positive infinity.
Beautiful. Now, what if I give you the null set? Or what if I give you the empty set? What would I shade?
Nothing.
Nothing, right? And there would be no interval to represent that. It's empty. There's nothing there. Again, don't ever put the null set inside of the empty set. That is kind of a nonsensical thing in math. I will laugh. So what have we learned? Open means parentheses, whether it's left or right. Closed means bracket, whether left or right. That's how the graph corresponds to the interval notation. All right, moving on. Let's go ahead and utilize all this information and look at two sets at the same time. But now we're going to look at union or intersection. So in the first example, I have been given two intervals. And I'm looking at the union of these two intervals. So union is OR. So if I'm looking at the union of sets, I'm looking at all possible values. If it's in one of the sets, it's in the solution set. Now, I have given you three number lines, because some people like to graph one, then graph the other interval, and then look at the union or the intersection. You don't have to graph all three. I'm going to graph all three for you to make sure you understand how we're arriving at the union. You will be provided with three on the test and quiz, but I won't necessarily have to look at all three, just the solution set. So let's look at the first interval. The first interval is from -3 to 4. So I'm going to align my three graphs. So my first interval, open -3, open 4, and I'm shading everything in between. My second set is represented by this interval. So I'm going to go from 3 to 7. They're both going to be open endpoints, and I'm shading everything in between. Now, if I'm looking for the union, I'm looking for all possible values. So union would go from where to where? -3 to 7, and the endpoints would be open. So this final graph is the solution set. How would I represent the solution? As an interval?
-3, 7.
Open, -3, open 7. So again, you don't have to show me these two, but if it helps you determine the union or the intersection,
How would
by
you
all
show it?
means.
How would you show it in set notation?
In set builder notation, I like that you asked that. It would be all values x such that x is in between -3 and 7. You can have this inside set builder notation. And we're going to talk about that notation a little bit later. Okay, let's look at the second example. This is my first interval. So again, from -3 to 4, both endpoints open, shading everything in between. Second interval, again, is from 3 to 7. Endpoints are open. But now, what am I looking at? I'm looking at the intersection. So you have to be able to recognize which is which. So in this case, I'm looking at the intersection That means and implies only what is shared. What do they have in common? So if I were to graph this solution set, what would it be?
3,
3, 4.
3 to 4 with both endpoints open.
Why open?
Well, because 3 is not included in this one, 4 is not included in this one. And remember, they have to be in both for it to be an and. So my solution as an interval would be 3 to 4. Now, looking at the next example, I noticed that in the first interval, the 4 is closed. So I still am going from -3 to 4. 3 is open, 4 is closed. The second interval,
Scroll down, please. Thank you.
of course, is 3 to 7, but in this case, the 3 is closed, the 7 is open. So now, am I looking at union or intersection?
Union.
I'm looking at the union, so what would the union be?
Open -3, open 7.
Excellent. And shading everything in between. So this solution set would be -3 to 7. Now looking at the next one, we see same first interval, -3 to 4. 3 is open. No, sorry, -3 is open, 4 is closed. The second set is from 3 to 7, where 3 is closed and 7 is open. Bless you. So, am I looking for union or intersection? Intersection. What is the intersection of those two sets?
Closed 3, closed 4.
Close 3, close 4. And shading everything in between. Colin, do you see the difference?
Yes, ma'am.
Okay. So close 3, close 4. Now, looking at the next one, I'm going from -infinity to 4.
Scroll down, please.
4 is closed. And I'm shading everything to the left because that's -infinity. The second interval, where's my green? Where did my green go? There. Is from 3 to +infinity. 3 is closed. Shading to the right, +infinity. Am I looking for union or intersection?
Union.
I'm looking for union. So what is the union of these two sets?
-infinity, positive.
The entire real number line. Yes, -infinity to +infinity. Excellent. Does it help to draw the other two?
No.
No? Okay. All right. In the sixth example, I'm going from -infinity to 4. 4 is closed. Shading to the left. The second interval is 3 closed to +infinity. Am I looking for union or intersection?
Intersection.
And what is the intersection of these two sets?
3, 4, close.
Both closed, yes.
Okay.
So my solution set close 3 to close 4.
Wait, so like for number 5, if you were to put that in set builder notation, would it just be like -infinity is less than x, and then
You can do it that way. There's many ways to do set builder notation.
but
So-
it still works like just
Yeah,
using
I could, in fact, do this, yes. Or I could say x could be any number such that x is an element of the reals. Ooh,
Ooh.
fancy.
I don't like that.
You don't like it?
No, it was on like some
It's too
Like-
fancy.
a review for one of the units on my math class. and I was very confused.
Yeah, I just.
Now, while we solve linear inequalities, we have to keep some properties in mind. Now, I think they're kind of obvious, but let's go ahead and reinforce them formally. You have been given three real numbers represented by A, B, and C. They are elements of the real. So A, B, and C are just real numbers. I have also been told that A is less than B. Bless you. So if I keep that in mind and I say, okay, A is less than B. So this is what I'm starting with. A is less than B. The addition property states, the addition property of inequality states, bless you, that if I add another real number C to both sides of the inequality, I don't change the inequality. A plus some number C is less than B than plus some number C if A is less than B. I'm adding the same thing to both sides, nothing changes in terms of the inequality. Makes sense?
Yeah.
Now, the next property says, okay, again, A is less than B. And if I multiply by a positive number, so this is the positive multiplication property of inequalities, if I multiply each side by a positive number, that still doesn't change the inequality, the relationship between A and B. Makes sense. However, if I multiply or divide, since they're opposite operations, if I multiply or divide by a negative number across the inequality, the negative multiplication property of inequality says I must change the direction of the inequality. So while I have A and B, if I multiply by a negative number, so C, I'll define C to be negative here. I will define C to be positive here. If I multiply both sides by a negative number, I am changing the direction of the inequality. If you multiply or divide by a negative number across an inequality, the direction of the inequality changes. We saw that when we were solving absolute value inequalities, which we will do more of. So let's see if we can utilize those properties. You have a nice little linear inequality here. How would I go about solving for x so I could graph the solution set?
-5.
Hmm?
-5.
Subtract 5 from both sides. Okay, so that's going to give me 2x is less than 12. I keep going, and what would I do next?
Divided by 2.
I divide both sides by 2. And my answer as an inequality is x is less than 6. So there's my solution as an inequality. If I wanted to graph my solution set, I would show 0 because I like to see 0. So I know you know whether you're dealing with positive or negative numbers. So 0 is a nice, stable point. 1, 2, 3, 4, 5, 6. Is it going to be open or closed?
Open.
Open. In which direction am I going to shade? To the left. So there is my graph of my solution set. Well, let's go ahead and represent it as an interval. What would the interval that corresponds to the solution set be?
Negative infinity 6.
Excellent, both open. And for kicks, if we wanted to do set builder notation,
X,
x is any number such that,
any number such that x is less than 6.
beautiful. So you should feel comfortable, right? You can solve it, but then I may ask you to represent it in certain forms. Okay, what about the next one? How would I go about solving for x here?
Dividing by negative.
Oh, I'm dividing by
So
negative.
you have to
Oh.
switch the
I divided by a negative across the inequality, so I have to change the direction of the inequality. This now becomes greater than or equal to negative 6. So here is my solution as an inequality. If I wanted to graph it, again, I like to see 0. Negative 1, 2, 3, 4, 5, 6. And what's happening at negative 6?
It's
Open or closed?
Close.
It is closed. In which direction am I shading?
to the right.
If you solve for the variable on the left, you shade the direction the inequality is pointing. And as an interval,
Close -6, infinity.
and similarly in set builder notation, x can be any number such that x is greater than or equal to negative 6. Now, the problems are not going to be that easy. They're going to be much more fun than that. We're going to have lots of operations we have to do to solve for x. But at some point, you get to a point in the problem where you can easily identify what the solution set is going to be. So let's say we're doing all these algebraic operations and we arrive to this point. I want to solve for x. So what might I do at this next stage to solve for x?
Subtract by x.
Subtract x from both sides. Now, if I subtract x from both sides, I'm going to get 0 is less than 1,
Which is true. but
which is always true. I don't care what x value you give me. This statement, 0 is less than 1, is always going to be true. So what is the solution set if we arrive at something that is always true?
all real numbers.
All real numbers. In interval form, negative infinity to positive infinity. So if you arrive at a point where you have a statement that is always true, 3 is less than 10, whatever it is, if it's always true, your solution set is all real numbers.
What if it's never true?
Well, that's going to be the very next example.
Well, call it.
Imagine that, how I plan these notes to make you think and follow a certain thought process. I love it. So at this point, we would subtract x from both sides, but then I'm going to get 0 is greater than 1. I have a contradiction. As soon as you get a false statement, I don't care what x value you try to put in there, it is never going to be true. So what does that imply? There is no solution. The null set, the empty set, it's never going to be true. You cannot give me an x that will make that true. 0 is never greater than 1. Now, we talked about union and intersection. How are we going to maybe think about that in different formats? Well, there is something called a compound inequality, also known as an extended inequality. We utilize this format when we are dealing with an intersection, with and. It is only used for and. Why? Because I can take two linear inequalities and compound them. I can put them together in one extended inequality. So let's go ahead and solve each of them independently and see how we would represent our answer as a compound inequality. If I'm solving for x, what would I do to each of these inequalities?
Never mind. Subtract 1.
I would subtract 1. No matter which one I'm solving, my first step would be to subtract 1. So that would give me negative 4 is less than 2x, and 2x is less than or equal to 2. Next step in each of these.
About 2.
Divide each side of the inequalities by 2. So that would give me -2 is less than x, and you have to write and or, because it makes a difference. And x is less than or equal to 1. Now, there is my solution. That is fine. Algebraically, we've solved for the values of x that make this true. However, this lends itself to this extended inequality where I can rewrite this as -2 is less than x and less than 1. Do you see how I've put those together?
Yeah.
That is an extended inequality.
And you can solve them. And they're really fun.
Well, there's nothing to solve. That's the
Well,
solution.
later. The
But
next
this
problem.
makes it very easy for us to perhaps identify the corresponding interval. What would the corresponding interval be?
-2.
And this also lends itself to beautifully identifying the graph. -1, 0, 1. It would be closed at 1, open at -2, and shading all the x's in between. So, when you get to this point, we do want to go one step further and represent it as an extended inequality, and we do want to be able to show the interval and graph the solution set. Now, I'm going to show you that these are the same exact problem. This and allows me to put this in the middle of the compound inequality and solve it all at once. -3 is less than 2x plus 1, and at the same time, 2x plus 1 is less than or equal to 3. Do you see how these are the same exact problem? Okay, so I'm still going to subtract 1 from every component of that inequality. That would give me -4 is less than 2x is less than or equal to 2. I'm still going to try to isolate that little x by dividing every component by 2. That again is going to give me -2 is less than x is less than or equal to 1. I get the same answer. It is beautiful. Now, some people like to solve it separately. Some people prefer to solve it at once as a compound inequality. I really don't care. You may have I have a personal preference. I like to do it all at once. It's pretty that way. I don't care. Now, in this case, I have an or. So I'm going to go ahead and solve each of them independently. Subtracting 1, like we did in the previous examples, but now this is an or.
Go down.
This is going to give me -4 is less than 2x, or 2x is less than or equal to 2. I'm still going to continue to solve for x by dividing every component by 2. -2 is less than x, or x is less than or equal to 1. Now, while I cannot put this as an extended inequality, because for extended inequalities, they both have to be going the same direction and they both have to be less than. The smaller number has to be to the left, or else it's a nonsense statement. So perhaps now, to adequately, because this is not a final answer, we have to think about how we would graph the solution set and what the solution set really is. A more sophisticated way of representing the solution set. So at this point, if you want to go ahead and do them separately, like we did in the past, we can. So I can look at this and say, oh, I can write that as x is greater than -2. So maybe my first graph would show that x is greater than -2. My second one would be x is less than or equal to 1. But this is an or statement. So for the union, what would the solution set really be?
Infinite negative.
The whole real number line. So our real solution, no pun intended.
Why is it different?
I'm sorry? It's yeah, beautiful, Henry. It's every possible solution. These overlap, right? This is an or. So this isn't good enough. This is really the best way to represent your answer. And this is your graph. Now, let's go ahead and solve this one. Subtract 1 from everything. Negative 4 is less than negative 2x is less than or equal to 2. I divide every component of the inequality by 2. I get negative 2 is less than x is less than or equal to 1. Is that true? No, because I'm dividing by a negative. So if I'm dividing by a negative, what's happening? I have to change the direction of the inequalities. Now, what did we say about extended inequalities?
Can you scroll
They
back?
have to be all the same direction and less than.
And less than. Can you be a number that is less than negative 2 and greater than or equal to 1 at the same time?
No, wait a minute, hold up.
This is a negative. And this is a positive. Golly. Yes.
You can't.
So let's rewrite this, shall we? With less than. Negative 1 is less than or equal to x is less than 2. Is that true?
Yeah.
Yes, it is. Can you give me this as an answer?
No.
No. I have to have it in this form. You can't have greater thans. That's nonsense. Graph, negative 1, 0, 1, 2. Closed at negative 1, open at 2, shading everything in between. As an interval, closed negative 1, open 2. We're feeling good?
Yes.
All right. Let's now take these rules and solving these linear inequalities and embed them in absolute value inequalities. We just keep building on it and building on it. Now, you've seen this before. We've solved absolute value equalities. Let's talk about how we're going to solve absolute value inequalities. We know absolute value represents distance. So let's talk about how we would read these inequalities. I'm looking at the distance between those two numbers, x and a, but in this case, the distance has to be less than c units away. So that means I'm starting at a, and I'm traveling c units in either direction, and I'm shading everything up to that c unit away. In this case, I have the distance between x and a has to be greater than or equal to, in this case, c units away. So I start at a, I travel c units, and then I start shading everything that's further greater than c units away. A little bit of shading going on. So let's look at this example. This example says that graphically, I'm looking at the distance between x and 2. So I'm looking for all x's away from 2 that are less than 3 units away. So I start at 2. That's my A. I know that I'm worried about being 3 units away. So I go 3 units this way and 3 units this way. However, I'm looking for all x's that are less than 3 units away from 2. So what is that going to be? All the way up here, and then I stop. Because anything past that point is more than 3 units away. From 2, I'm going to go to the left 3 units and stop. Because I can only be 3 units away, less than up to 3 units away in either direction. Do you see how I arrive at this answer? Okay.
What would the solution set be?
So the solution set to this would just be
-1 and 5?
-1 to 5, open,
Okay.
right? Because it's just this little interval. Okay, let's look at this example. Now remember, graphically, we're doing these graphically first. Graphically, if I want to represent this, what might I want to do first inside?
Put it into the negative.
That's right, x minus a. So perhaps to be able to graph this, I want to rewrite this as x minus -2 is greater than 3. This allows me to easily identify a. What is a?
-2.
-2. So I'm at -2. Now, I'm looking at all x values that are greater than 3 units away. So I'm going to go 3 units to the right, 3 units to the left, and from those points, I will shade everything that is greater than those 3 units away. Does everybody see how I arrived at this graph? I start at -2, and I'm looking at all x's that are more than 3 units away. If I'm here, I'm less than 3 units away. If I'm here, I'm equal to 3 units away. Anything further is more than 3 units away. So how would I represent the solution as in interval form?
-infinity, open 3, union
Open,
3.
open,
Negative. No.
open.
-1. I can't do simple. Alright.
What would this endpoint be?
Henry just said it. -5.
-5, okay. And it's open. Union! What's this point?
1.
Yes. So 1 to positive.
Okay.
Now notice, this is union. This is associated with the greater than symbol. And I misspelled that on purpose. When you have your absolute value expression isolated on the left of the inequality,
Oh, great.
if it's a greater than, it's going to be a union.
That's actually really cool.
Now, looking at this next example, again, perhaps we want to rewrite it as a subtraction as a distance. That easily allows me to identify where my little mid-starting point is on the graph, so that -2. And I'm looking at all values that are less than or equal to 3 units away. So 3 units this direction, 3 units this direction, again, gets me to -5 and 1. But I'm looking at all x values that are less than or equal to 3 units away. So I'm traveling 3 units in either direction and stopping once I get that far. This is a beautiful little interval. How would I represent this solution?
-5,
1, close.
Yes. Now notice, this is a less than sign.
Oh, wow.
It is an intersection. So once you have your absolute value expression isolated on one side of the inequality, if it is a less than symbol, it's going to be an intersection. It's just this interval. Now, let's look at the next example. Anybody have any reaction to this?
-3. No.
No solution.
Absolute value is never negative. So is this statement ever going to be true? No, because once I take the absolute value, heaven forbid, I'm not only not ever going to be less than or equal to -3, I'm never going to be less than 0. So in this case, there is not a thing for you to do on that quiz. There is no solution. There is nothing for you to do. Don't you even start rewriting that and graphing it and trying to travel and do. You're wasting your time. You should be able to recognize this in your heart of hearts. This is never true. Now, let's look at the next one. Absolute value of x plus 2 greater than or equal to -3.
No.
But it's greater than.
But it's greater than. When is this true?
When it's more or greater than 0 as well.
When is this true? When is this statement true?
Always.
Always!
1.
Because the absolute value is always going to be greater than -3. Period. Period. Because once I take the absolute value, it's positive. A positive number is always going to be greater than a negative number. So this is always true. All real numbers.
Can you scroll down?
Yes. Never true, always true. You need to know the difference. Now, in the next example, I have my absolute value isolated. I could graph this. I'm looking at all values that are greater than or equal to 3 units away. So first of all, is this an and or an or? Great or.
Right.
So it's a union. What is the graph going to look like? Graph. What's happening at these endpoints? Open or closed?
Close.
In which direction am I shading? Outward, right?
Yeah.
How would I write the solution?
Negative infinity.
-infinity to
-3.
Oh.
Close.
closed. Union. I need to see that union sign. Beautiful. These are fun. I like them. Next one. I'm looking at less than. So what does that mean? And intersection. So I'm going all the way up to 3, not including 3. Distance in the opposite direction, 3 to -3. So how would I represent this solution set?
X.
Right?
Yeah.
I could also write it if I wanted to.
Yeah.
Now, before you start graphing, before you even start thinking about is it less than or greater than, you gotta isolate the absolute value expression on one side. So what would I do first?
Add 5.
Okay. That would give me 2 times the absolute value of x minus 1 is greater than 8. Next step.
Divide by 2.
Okay. That would give me the absolute value of x minus 1 is greater than 4. It is at this point you then determine, is it an and or is it an or? Because we don't know what algebraic operations we're doing to get it to this point. It is great or. So it is a union. And at what point am I starting on the number line?
-1.
No.
No, -1.
Just 1.
Just 1. and I'm traveling 4 units in either direction, and I'm looking at all x values that are greater than 4 units away. So what is this solution set going to be in interval form?
Negative infinity 1. Oh, yeah.
Union, no,
I mean,
yes.
good.
Good. Now, we did them graphically. Let's talk about how we can do it quick and easy algebraically, because we don't have to turn these into subtraction and find the little middle point and then travel in different directions. We can just do it algebraically. Just like we did with absolute value equations, we can have the 2 cases. The inside could be positive, the inside could be negative. So we have to address both. How did we do that with an equality? We set it equal to the positive and the negative. How did we arrive at that? By dropping the absolute value, setting it equal to the positive, but then taking the opposite,
So you switch the direction.
and you have to switch the direction of the inequality when you take the opposite. Why? Because you are multiplying then dividing by a negative number. So if I am starting with this inequality, absolute value of x minus 2 is less than 3. I can drop the absolute value and just solve the problem as is. And I can get a solution. However, I have to address the opposite. So once I introduce this opposite and I divide across the inequality by a negative number, I am now solving this. Now, people have a tendency to go from here and just jump and write both of these. That is fine, but you need to know where they're coming from. We're changing the direction of the inequality when we're turning it into a negative. Now, knowing what we know about less than, is this an and or an or?
Or.
Which one, the second one?
And.
Bruce, what was the second one? And.
This is an and. So when I split it into these 2 inequalities that I'm solving, I can either put it as a compound inequality and solve it all at once, or I could separate it into 2, and I could solve them independently and then take the intersection of the solution. So how would I rewrite this? Using an extended inequality. So instead of just splitting it into 2, I could have also written this as x minus 2 is less than 3, but at the same time greater than negative 3. This is the same thing as writing them separately and connecting it with an and.
Can you explain that again? Because I don't understand how you did that.
X minus 2 is less than 3, and at the same time, x minus 2 is greater than negative 3. So you can drop the absolute value, change the sign, and just perpetuate the inequality and solve it at once. Solving these together with an and, or solving it as a compound inequality, is the same thing. Just like we saw here. We just added an absolute value. It is nice. Let's look at some examples. You're being asked to solve for x. I have my absolute value. We're doing this algebraically, not geometrically right now. I'm looking at the inequality, and I'm trying to decide, is it an and or an or?
Less than.
It's less than. Since it is an and, I can combine them, right? Or I could solve them separately. We're going to do it both ways, and then you decide your favorite. So I could say x plus 2 is less than or equal to 3, and x plus 2 is greater than or equal to negative 3, right?
Yeah.
Change the direction of the inequality when I change the sign. I could go about my business, solving for x, like we know how to do. I could get x is less than or equal to 1, and x is greater than or equal to -5. Now, algebraically, that is correct. However, we'd want to go a little bit further. To demonstrate how easy it is to go further, if you write it as a compound inequality, x plus 2 is less than or equal to 3, but greater than or equal to -3. These are the same thing. They mean the same thing. I could then solve this one at the same time, giving me, oops, that's a 2. -5 is less than or equal to x is less than or equal to 1. Now that's easy to graph, isn't it?
Mm-hmm.
Yeah. -5, I like to see 0, 1. Open or closed at these endpoints? And am I shading in between or outward?
Out.
And as an interval, what would it be? So we would have to go further and write this as an extended inequality and then be able to do it this way. So I don't know what you like to do. Personally, I do it this way. It's up to you. Now let's look at the next one. Is it an and or an or?
Yeah.
It's an and.
But there's zero.
Wait a minute.
So it would kind of be nonsense because 0 is neither positive or negative, so I can't really write it as a compound inequality. Right, because that would be silly.
Yeah.
So I'm going to split it and kind of investigate a little bit further. So I have x plus 2 is less than 0 and x plus 2 is greater than 0. Okay. I must solve each of these. And I'm going to get x is less than -2 and x is greater than -2.
Wait a minute.
Now, and means they have to satisfy both at the same time. Let me go ahead and graph it because I'm still a little unsure as to what's going on. So in my first graph, I'm going to be at -2. And am I going to be open or closed?
Okay.
Open, and I'm going to shade which direction?
To the left.
To the left. Okay, now let me go ahead and graph this one.
Hold down a little bit.
I'm open at -2 and I'm shading to the right. And do we have anything in common?
No.
No. We can't be less than -2 and greater than -2 at the same time. So we have no solution. Right? So there's shortcuts to solving inequalities when you think about it as distances. If I have less than, we said that we could write it as a compound inequality, so we know in general that we're looking at an interval, right? Whether they're open or closed, it doesn't matter, but we're in an interval. If it is a greater than statement, it is or. Most often, we're looking at two pieces. There are exceptions. There can be no solution. There can be all real numbers. We can just go one direction. But in general, this is how we're thinking about it. So looking at this, is it an and or an or? It is an and, less than. But let's see what happens. Do we want to write it as a compound inequality?
No.
You can't really.
We can't?
Not really. You can't
Well,
really
it's
have -0.
equal also.
All right, well then let's go ahead and separate it if you really want to. And I'm going to solve for x. And I'm going to get x is less than or equal to negative 2 and x is greater than or equal to negative 2. Do we need to graph them separately? See what's going on? No?
Oh, and equal to, so it's just negative.
Yeah.
It's everything. Ooh.
I don't know. I think we're gonna have to graph it because I'm not feeling it from you.
No, I got it.
Okay, so I'm at negative 2. What's happening at negative 2 for this?
Closed circle
Closed.
going to the
Okay. Now let's look at this component. I'm at negative 2. What's happening at negative 2?
closed circle over to the right.
This is an and.
So it's just negative 2.
So your solution is just the point negative 2. Do you see this? That or equal to changed everything, right? Because in the previous example, it wasn't or equal to. You can't be less than and greater than, but you could be equal. In
So if
both.
one of them was equal to and one of them was not equal to,
Doesn't matter. Not for an and. Okay, let's look at this one. Is it an and or an or?
Or
It is an or. Ooh, okay. So I'm going to go ahead and split it. X plus 2 is greater than 0 or x plus 2 is less than 0. Subtract 2 from both sides. And I have x is greater than negative 2 or x is less than negative 2.
that can just be any real number besides negative 2.
Except for negative 2, right? Do we need to see that separately? No, yes?
No.
Well, I'm doing it anyway, too bad.
Oh, no.
Negative 2, open to the right. In this case, negative 2, open and to the left. This is an or, so all possible solutions,
Except negative 2.
right?
That lonely little negative.
Lonely little negative 2. How would I represent the solution set as an interval? And you are using interval notation.
Interval.
negative infinity, negative 2 union, negative 2.
Yes. Aren't these exciting? I mean, my gosh, they're just so little bitty little things that change from here to there. Okay, look at the next one.
Or
It is or. Do I have to do any work in this one?
really.
Absolute value of x plus 2 greater than or equal to 0. It is all real numbers. This is always true. It's not a thing to do on this problem. Don't waste your time on the test. You don't have time for that. Right? This statement's always true. I don't have to do anything algebraically. What about this one? This is an and. Look at the statement. No solution. There's no work to be done on this one either. Don't waste your time. I can't. It shocks me when I see people start splitting this and then doing this, graphing it, and I'm like, what are you doing? It's never negative. What about this one? All real numbers. Are you getting a hang of these?
Yes.
Okay. Look at the next one. Okay. Is it an and or an or? Great or than. It's a union. So I'm going to split it. X minus a half is greater than 4 or x minus a half is less than negative 4. Oh, fraction. Common denominator. I like improper fractions. This is going to be x is greater than what? Improper fraction.
9.
9 halves.
That's
Or x is less than what?
Seven halves. No. Six. No.
Negative
Eight.
7 halves.
Yeah.
No.
Yeah.
Yes, that's right.
Okay, let's think about these graphs. We can graph these independently, but you should at this point be able to immediately tell me the solution set. If you need to graph them independently, go for it. Tell me the solution set in interval form. This is sufficient as an inequality.
negative infinity.
No.
Negative 7 halves.
Yes.
Union.
Union.
Or
Negative
No,
2
9
infinity.
halves. 9 halves infinity.
Do we see that? This is shading to the left. This is shading to the right, but this number is to the left of this one. We see that it's like this, right?
Yes. That makes sense.
Okay. Is this and or?
And
Ooh. That is.
Less than. So I'm going to write it as a compound inequality. Why not? I like it like that. Add 1. Have no fear of the decimals. So this is going to give me negative 1.5 is less than x is less than 3.5. I love that notation. I can tell you the interval immediately. What is it?
Negative 1.5. Open. 3.5.
Beautiful.
I do love that one.
You know, it is lovely. It is lovely.
You
Only
gotta
work-
do it.
only-
I would rather do like that. You gotta do it.
If it's an and, I would, yeah. Okay, now they get more interesting. We've seen this one. What do we do first? Add 5. Again, don't you look at that inequality until you've isolated the absolute value expression on one side of the inequality. It is then and only then that you determine if it's an and or an or.
Fractions.
Next step, divide by 2. I have the absolute value of x minus 1 is greater than or equal to 4. You can now tell me, is it an and or is it an or?
It's an or.
Or. So I'm separating it. I have x minus 1 is greater than or equal to 4, or x minus 1 is less than or equal to negative 4. I'm solving each of them independently. I'm getting x is greater than or equal to 5, or I need to see that. If you don't write and or, I'm going to assume you don't know the difference. And mark it just completely wrong, no partial credit.
negative.
Okay, so while this works, we want to be able to write it as an interval. What is the interval?
negative 3. Infinity negative 3.
Union.
5. Infinity.
And we could graph it. Last but not least, what do I do first? Okay, that's negative 2 times the absolute value of x minus 1 is greater than or equal to 8. Next step. Oh. I'm dividing by a negative across the inequality. I have to change the direction of that inequality so it becomes a greater than or equal to negative 4. It is at this point.
Less than.
Yeah.
Oh, yes. Got all excited by switching it and didn't switch it. So, is this an and or is it an or?
And.
It is an and. Ha! You see?
Yeah.
Wait until you isolate the absolute value expression, then determine, or it's all off. Oh, it says it's an and. What can I do? Oh, but do I have to do anything?
No, wait a minute.
I know this is no solution. Fun. Okay. You have my math lab, lots of my math lab. So we've done 1.7a and b. We're a day ahead. Tomorrow we're doing 5.5.
Are we gonna do the PSAT stuff? Should we be bringing our booklets?
No, you need to do, I gave you the sheet, you
Okay.
just do it. If you have questions, you ask.